Hello, in this video I'm going to show you how to solve this problem involving using cold water for and heat for power generation. It doesn't really matter whether this power generation comes from nuclear or coal. Basically, either way, you have a hot reservoir and a cold reservoir. And the heat engine operates between the two. It takes heat from the hot, puts some of it into the cold, and does work with the rest. In this particular problem, we are told that the hot reservoir is at 570 degrees C, and the cold reservoir is at 30 degrees C. And we are the first thing we would like to know is what is the maximum efficiency of this engine? How much work can we get out per heat we put in? So I'm going to use the formula we had in class as well as in the book, which is the maximum possible efficiency of a heat engine is 1 minus T cold over T hot. We can't just stick in the values in degrees C because you have to use degrees Kelvin. So if we convert 570 to 570 to Kelvin, we have to add 273. We get 843.15. 843. We'll just stick it there. We won't worry about the 15. We do the 273 plus 30. We get 330. So basically, the hot temperature is 843 Kelvin. The cold temperature is 303 Kelvin. That gives us a efficiency of about 0.64. Or said differently, 64%. Say that the efficiency of this power plant, whether it's a coal plant or nuclear plant, is 64%. This is actually really good. Real power plants aren't 64% efficient. Obviously, they're less efficient than the maximum possible efficiency. More common efficiency are like 30 to 40%. But gives you an idea. Okay, number 2. Suppose we're going to pretend we're running at maximum possible efficiency, so 64%. In order to produce 1.0 times 10 to the 8th joules of electricity, that's about U.S. daily consumption per consumer. How much heat, whether the heat is coming from coal or nuclear, how much heat do you need? Okay, so where do we get this? Okay, so we need we basically remember that efficiency is defined in this case as the thing we want, that is work out over the thing we have to put in, Q hot. We want to know Q hot, so Q hot is equal to work over efficiency. The work we want out, the amount of electricity, is 1.0 times 10 to the 8th joules. Divide that by 0.64, and we get 1.56 times 10 to the 8th joules. So that tells us how much heat we have to put in, how much heat from coal or nuclear or natural gas needs to be put in to get this much, to get 1 day's for one person's electricity out. Okay. You may notice that this 1.56 is bigger than 1.0. Basically, you have to put in more heat than you end up getting out in electricity because some of it goes to the cold end. Which brings us to question number 3. Question number 3 is how much heat is expelled to the cold reservoir? So if you look at your picture, we have heat coming in from the hot. Some of it goes to work and some of it goes to cold. So we can write this as Q hot equals work plus Q cold. We're looking for Q cold, so Q cold We want to know how much waste heat end up going to the cold end. That's Q cold is equal to Q hot minus work. Q hot is 1.656 times 10 to the 8th joules minus the work, which is the amount of electricity we got out, which is 1.0 times 10 to the 8th joules. And we see the difference goes to the cold reservoir, which is 5.6 times 10 to the 7th joules. It's the extra 0.56 there. Okay, so that's how much waste heat goes to the cold reservoir. And the final question is, suppose that this waste heat is used, it basically goes into heating ocean water. So suppose you got your power plants by the ocean, it's taking in cold water from the ocean at 10 degrees C, and it's heating it up to 30 degrees C, the cold end of your power plant. How much water will you heat? Basically, in order to produce electricity for one person or one customer for one day, how much water will you heat? Okay, so question number 4. So let's see, Q equals MC delta T, and we're asked what volume of water let's see here. So we want to find the volume. So volume is related to mass by density. Density is mass over volume. We can replace mass, so we get Q is equal to rho VC delta T. We know the heat, this is Q cold basically. It's the heat we're dumping to the cold end goes into heating water, MC delta T of water. C is a specific heat. Delta T is how much the water heated up. So that would be like from 10 to 30 degrees C. We know density of water, and the specific heat of water all known. We're looking for volume, so let's solve for volume. Volume is equal to Q cold over rho C delta T. We can put that together with numbers. We can have Q cold is 5.6 times 10 to the 7th joules over the density, which is density of water is easy. It's 1.0 grams per cubic centimeter. The specific heat of water, 4.184 joules per gram, degrees C or degrees Kelvin. And our change in temperature is 30 degrees C minus 10 degrees C. And because that's a difference in temperature, it can cancel out with the Kelvin there. Alternatively, we can just write that as degrees C. Okay, so that is the numbers there. We're going to need we're going to need unit conversion to convert to centimeters. So now if we do 100 centimeters per meter cubed, if we want to get the answer in cubic meters, then we get our joules cancel, our grams cancel, our centimeters cubed cancels, our degrees C cancels, and we're left with cubic meters. If I did this calculation right, then that comes out to about 0.6 cubic meters. In other words, to produce the electricity for one customer for one day, you need to heat about 0.6 cubic meters. Now, remember, a meter is this, so a cubic meter is like a box of water, yay big. And you need to, heat roughly half of that, or 60% of that in one day as the waste heat from the power plant, which is, I guess that gives you an idea of how much cold water needs to flow in the power plant. Thanks for watching.